previous lecture, we had discussed the Heisenberg's uncertainty principle, in which we ultimately concluded that uncertainty principle is not considered for simultaneous measurement of the position and momentum of large objects in daily life. Moving further to the time-independent Schrodinger's wave equation. In 1927, Schrödinger developed a mathematical wave equation to describe the wave motion of the electron in a hydrogen atom. He considered that the nucleus is surrounded by a vibrating electron wave and compared it with a stationary wave. You all must have read about the Schrödinger wave equation, in which Hamiltonian operator H psi is equal to E psi. But now we'll study the Schrödinger wave equation in the Cartesian coordinates. We are not going to do the derivation of this equation. It is only that we have to learn about the Schrödinger wave equation's basic concepts. It is given by d2 psi upon dx square plus d2 psi upon dy square plus d2 psi upon dz square plus 8 pi square m upon h square E minus V psi is equal to 0. Here x, y, z are the Cartesian coordinates. In polar coordinates, this equation is there on your screen. Psi is the amplitude of wave, E stands for the total energy, V stands for the potential energy, m stands for the mass of electron. X, Y, Z are the Cartesian coordinates, which are related to the polar coordinates r, theta and phi, as shown here on the screen. Let us discuss the physical significance of wave function psi and psi square. Psi has only mathematical significance, and we do not attach any physical significance to psi. When the wave amplitude is large, the probability of the event is large, and when the amplitude is small, the probability of the event is comparatively small. Wave function psi itself cannot represent such a probability, since this would mean that psi should always be a real valued function. That means psi should always be 0 or positive, but it is not so. Actually, psi in some cases is a complex function, that is, it contains imaginary numbers. Therefore, we must look for square of wave function psi square. Psi square represents intensity. Greater the intensity of wave function at a particular point, greater is the probability of locating the electron at that point. Thus, psi square may be interpreted as being proportional to electron density. When psi square is high, electron density is also high. Psi star is used in place of psi square. Psi star is the complex conjugate of psi. We expect that if psi extends over a finite volume in space, that is dx dy dz is equal to d tau, then the electron would be found in that volume. So, psi square d tau gives the probability of finding the electron in the volume d tau. If psi has a real value, then psi is equal to psi star, and we can use psi square d tau in place of psi square d tau. The wave function psi may be positive, negative or imaginary, but the probability density, that means psi star, will always be positive and real. The probability of finding the electron is finite, which means psi star d tau must give real values. Conditions wave functions must obey to give meaningful results. Number one is that psi must be single valued, that is, it must have only one definite value at a particular point in space. Psi must be continuous at all points in space. That is, there must not be sudden changes in the values of psi when its variables are changed. Number 3, psi must have a finite value over the space d tau. Number 4, psi must be normalized, about which we will study in a while, and psi must become 0 at infinity. Now there are few terms which are very important to know here. Number 1 is the eigenfunctions. The significant values of psi are called the eigenfunctions or the wave function. Another term is the eigenvalue. Eigenfunctions give significant values of the total energy of electron, and these values are known as eigenvalues. These eigenvalues correspond to the discrete energy levels as postulated by Bohr in his model. This is mathematical representation of a normal wave function. A normalized wave function means that the probability of finding the electron in the given volume dx is equal to 1. If you remember, in the last slide we had used the volume d tau. That can also be used, and here when we are saying volume as dx, we will put the value dx. The wave function satisfying the following expression is said to be normalized. Psi square dx integral minus infinity to plus infinity is equal to 1. Another term is the orthogonal wave function. This means that a particular wave function must be different from all other wave function. In other words, they should be independent of each other. The word orthogonal means that the wave function do not overlap each other. They are independent of each other, just as two orthogonal vectors. Mathematically, orthogonal means perpendicular, and for perpendicular vectors, their dot product is 0. Similarly here, psi1, psi2 dot product over the volume dx integral comes out to be 0. Then it is known to follow orthogonality. If they also obey the equation of normalized wave function, they are said to be the normalized wave function. Psi1 star dx is equal to 1, psi2 star dx is equal to 1. Wave functions that are both normalized and orthogonal are known as orthonormal wave functions. Now, before moving further and talking about the Schrödinger wave equation, we first will talk about the quantum numbers and their significance. There are 4 quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. In the wave mechanics, the electron distribution in atom is divided into shells, which in turn are supposed to be having subshells, and those in turn are supposed to be made up of orbitals. Quantum numbers in general indicate the shell, the subshell, the orbital, and the electron. Let us talk about the principal quantum number. It identifies the shell or level in which electron is present. It designates the main energy level to which the electron belongs, represented by n. N can have a value 1, 2, 3 and so on. N is equal to 7 is the highest shell occupied by the known elements. It tells the average distance of the electron from the nucleus. Coming to the azimuthal quantum number, represented by L, it represents the subshell or sublevel of the shell in which the electron is present. It also denotes the angular momentum of an electron. Now, if the quantum number L is equal to 0, it is known as S subshell. L is equal to 1 is known as the P subshell. L is equal to 2 is known as the D subshell, and L is equal to 3 is known as the F subshell, and so on. Energy of subshells within a shell increases with the increasing value of L. Let us discuss few examples here. Say the principal quantum number is 1, then total values of L are equal to the number of n, that means 1. The values of L will be from 0 to n minus 1. Let us take the example of n is equal to 3. Total L will be 3. The values will be 0 to n minus 1, that means 0, 1 and 2, and they will be written as 3s, 3p, 3d. 3s means n is equal to 3, L is equal to 0. 3p means n is equal to 3, L is equal to 1. 3d means n is equal to 3 and L is equal to 2, and so on for the other orbits. Moving to the magnetic quantum number, it is represented by ml or sometimes only by m. It determines the possible quantized orientations of the orbitals in space. Let us take the example n is equal to 2. The values of L will be 0 and 1. Now coming to the values of magnetic quantum numbers, it will have the total values 2L plus 1. Putting the value of L for 0, we get 1. Putting the value of L is equal to 1, we get 3. Now the values range from minus L to 0 to plus L. Say when L is equal to 1, the ML will be minus 1, 0 and plus 1. Now number of orbitals come out to be 3. Each orbital can have 2 electrons each, so total will be 6 electrons. We'll take another example. Let us take the example of n is equal to 4. Here we can have 4 values of L, namely 0, 1, 2, 3. That means S, P, D and F. Now we calculate the value of magnetic quantum number for each of the orbital. We get, for L is equal to 0, we get M is equal to 0. For L is equal to 1, we get minus 1, 0 and plus 1. For L is equal to 2, we get minus 2, minus 1, 0, plus 1, plus 2. That means 5 orbitals. 4 dxy, 4 dyz, 4 dzx, 4 dx square minus y square and 4 dz square. When the value of L is equal to 3, then the values of ML will be from minus 3 to 0 to further up to plus 3. So we get 7 orbitals. So when n is equal to 4, that means when the principal quantum number is 4, we get total 16 orbitals and each orbital can have 2 electrons. So total 32 electrons can be accommodated. Moving to the spin quantum number, which is represented by ms, it arises from the spectral evidence that any electron revolving around the nucleus also will spin or rotate about its own axis and behave like a small magnet. The spinning can be clockwise or it can be anti-clockwise. Hence, for a given value of m, that means the magnetic quantum number, ms can have 2 values, that is plus half or minus half, and they are represented by 2 arrows in opposite direction. This spinning of electron affects the angular momentum and hence ultimately the energy. Now moving back to the Schrödinger wave equation, the solution of the Schrödinger wave equation in polar coordinates can be done by separating the 3 variables. The psi, which was dependent on 3 variables r, theta and phi, is assumed to be the product of 3 wave functions, each containing only one variable and can be represented like rr dot psi psi dot theta theta. Here rr represents radial dependence of wave function psi, theta theta and psi psi represent the angular dependence of the wave function psi. So we arrive at three independent equations, each having one variable. The solutions for these three differential equations obtained by separating of variables in polar coordinates are characterized by three quantum numbers: principal quantum number, azimuthal quantum number, and magnetic quantum number. Their dependence on quantum number is also shown in the following equation, which you can see in your screen. Out of these three functions, RR is called the radial wave function, whereas theta theta and phi phi are called the angular wave function. Let us talk about the radial wave function. RR gives the distribution of the electron with respect to its distance r from the nucleus. Here you can see RR versus R graphs, and in the second graph you can see the value of RR also goes down to a minimal, reaches a negative value and then rises. But when we come to the radial probability density, the square of the radial wave function, then you can see in the second graph on the screen that the negative portion is changed back to the positive portion after squaring. So the square graph, that means the radial probability density graph, only has the positive component. Now we move to the radial probability distribution curve, which are very important. These curves are obtained by plotting relative probabilities of finding electron in spherical shells at various distance from the nucleus. Here you can see a maxima. That region is known as HPR, that is the highest probability region, and the point where the value is 0 is known as the node. When we talk of different orbitals, for s orbitals, HPR, that means the high probability region, is equal to n and nodes are n minus 1. When p, the HPR is n minus 1 and nodes are n minus 2. For d orbital, HPR n minus 2 and nodes are n minus 3. And for f orbital, HPR is n minus 3 and nodes are n minus 4. We take the example here for 4s, 4p, 4d and 4f. Here you can see HPR, the high probability regions are 4 and the nodes are 3 in 4s. 4p, it is 3 and 2. For 4d, it is 2 and 1. And 4f, it is 1 and 0. The radial probability density is always small near the nucleus. You can see it is almost 0 there. For the same value of n, that is, here you can see it is for 3s, 3p and 3d. The n remains the same, it is equal to 3. The distance of maximum probability of various orbital is inversely dependent on the value of L, or the most probable distance decreases slightly as the azimuthal quantum number increases. For 3s, 3p and 3d, 3s L is equal to 0, 3p L is equal to 1, 3d L is equal to 2. Here in this plot also, this can be observed that the most probable distance is maximum for 3s. R maximum is called the radius of maximum probability. Penetration power of an orbital is a measure of its closeness to the nucleus. Due to the additional maxima in 3s curve, an electron in 3s spends some of its time more near the nucleus, making it to be more penetrating than 3p, which in turn is more penetrating than 3d. Talking about the angular wave function, it depends on L and M values and often referred as atomic orbitals. The shape of these orbitals depend on angles theta and phi, which determine the geometry of the atom. Value of this angular wave function for s orbital has no angular dependence, so it is spherically symmetrical, and probability of finding electron is equal in all directions for s orbital. The size of an s orbital depends upon value of the principal quantum number n. Greater is the value of n, larger is the size of the orbital. An important feature of the 2s orbital is that there is a spherical shell within this orbital where the probability of finding the electron is nearly 0. This is called node or the nodal surface. in 2s orbital, there is one spherical node. The number of nodal surfaces or nodes in s orbital of energy level is equal to n minus 1, where n is the principal quantum number. Using the component of angular wave function, p orbitals can have three possible orientations. These p orbitals are equal in energy, so they are known as having in degenerate state, but they differ in their orientations. They are oriented along the three axes. P orbitals have dumbbell shape and have directional character. It consists of two lobes symmetrical about a particular axis. The probability of finding electron is equal in both the lobes of p orbital. The p orbitals of higher energy levels have similar shapes, although their sizes are bigger. The two lobes of each p orbital are separated by a nodal plane which has zero electron density. D orbitals can have five orientations. They have the same shape, that is double dumbbell shaped, dxy, dyz and dzx, but they lie in different planes, namely xy, yz and zx. The dz square orbital is symmetrical about z-axis and has a dumbbell shape with a donut-shaped electron cloud in the center. The dx square minus y square orbital is also double dumbbell shaped, but its lobes are directed along the x and y axis. This is the 3D shape of the p orbitals, which are having one angular node, and d orbitals which are having two angular nodes. Now, as we move further, we have to explain the electronic configuration of different elements. For this, few rules are to be followed. Number one is the Pauli's exclusion principle, which was given by Pauli in 1925, which states that no two electrons can have an identical set of four quantum numbers, namely principal, azimuthal, magnetic and spin quantum numbers. Another point is that only two electrons can occupy the same orbital. The two electrons that are present in the same orbital must have opposite spins, or they should be anti-parallel. But now we take an example and say that we have three electrons in 1s orbital. Then four quantum numbers for each electron will be such that the third electron will have to be excluded. Say for the first electron, n is 1, l is 0, ml is 0 and ms is plus half. For the second electron again, n is 1, l is 0, ml is 0 and ms is minus half. For the third electron, n is 1, l is 0, ml is 0, then ms would be plus half or minus half, which would go against the Pauli's exclusion principle. So this is excluded, and in one orbital only two electrons can be present. Second is the Hund's rule of maximum multiplicity. This rule deals with the filling of electrons in degenerate orbitals of the same subshell, for example px, py and pz, or for the 5 orbitals of d. It states that electron pairing in p, d and f orbitals cannot occur until each orbital is singly occupied. Further, all singly occupied orbitals will have parallel spins. This can be explained through an example. We have boron, carbon, nitrogen and oxygen with atomic number 5, 6, 7 and 8. When we write the configuration, for boron it is 2p1, then 2p2, then 2p3 and then 2p4. 2p1 you can see here single electron, then 2p2, two unpaired electrons with parallel spin in p orbital, 2p3, three electrons parallel to each other, singly occupied, and when the fourth electron comes, now the pairing starts. Electrons will have minimum repulsion by occupying different degenerate orbitals, and also the two electrons with parallel spins in different orbitals will have less inter-electronic repulsions in space. and maximum multiplicity means that the total spin of all unpaired electrons is maximum. That is why it is known as Hund's rule of maximum multiplicity, which says that two electrons with parallel spins in different orbitals will be present. Last is the Aufbau principle. Aufbau means building up. In the ground state of atoms, the orbitals are filled in order of their increasing energies. Electrons first occupy the lowest energy orbitals available to them, 1s, 2s, 2p, 3s and so on. Alternatively, there is one n plus L rule which is also used. According to this rule, in neutral or isolated atom, lower is the value of n plus L, lower will be its energy and it will be filled first. But in case if the two orbitals have same value of n plus L, then the orbital with the lower value of n has lower energy. These are two exception configuration, means the half-filled and full-filled orbitals are stable. The reason given are, number one is the symmetrical distribution of electrons, and symmetry leads to stability. Second is the high exchange energy. The electrons which are there in degenerate orbitals have parallel spin and tend to exchange their position. Exchange energy is the energy released during this process. When the orbitals are half filled or completely filled, then the number of exchanges is maximum, therefore its stability is maximum. Here you can see when we come to atomic number 24 for chromium, it is 3d54s1. When it is half filled, there are 10 possible exchanges. On the other hand, if we write it as 3d44s2, there are only 6 exchanges, so it is more stable 3d54s1 form. These are the electronic configuration of first 30 elements, and here atomic number 24, which is the half-filled configuration, and atomic number 29, which is the full-filled configuration. They are the exceptional cases, and I have just told you the reason for the stability of half-filled and full-filled orbital. So dear learners, in today's topic of atomic structure, we have discussed the classical theories, the Rutherford scattering experiment, its drawbacks, Bohr's model, its drawbacks, then the de Broglie concept, then the Heisenberg's uncertainty principle and Schrodinger's wave equation. We have also studied the 4 quantum numbers and the rules for filling of the electronic configuration of the orbitals. And for this we have studied the Pauli's exclusion principle, we have talked about the Hund's rule of maximum multiplicity and also the Aufbau's principle. Thank you.